Hey kids, so this is our first unit. It's going to be on math for chemistry. And what I want you to think first is what happened here. So this was a cannon that I found. It's a picture I took in Athens. This is at the Acropolis. Turns out that structure was actually pretty well intact until it got bombed during one of the world wars. I think it was one, could have been two. But anyway, so this was a cannon that was there. And think about what happened there, and we'll get back to this in a second. So, accuracy versus precision. This is where we start. When you think about accuracy, accuracy is how close you are to something that's considered the accepted answer. And that's not the same as precision. So, precision is just how close your measurements are to each other. The classic way to explain this is the target. So, here we have a target and we have A, B, C, and D. And as you can see, if I asked you which of these targets were accurate, so which one was closest to the accepted answer, hopefully you could recognize that target A and target C are both accurate, right? They're getting close to that bullseye thing. If I asked you which were the most precise, which ones were just close together to each other, then B, right? You got a nice grouping here, and C is also precise. So another way to think about this is with sort of if you have someone shooting or kicking field goals or extra points, if the kicker is always kicking off by a little bit, that's still very precise, right? Precise, yes. Accurate, no. Is this a problem? Well, it just means there needs to be a minor adjustment so that you can move that into something where you start getting some points, right? So precise isn't awful, but it's not necessarily what we're looking for. Another way to look at this is if I gave some data and I tell you, let's say these two students were looking for the density of blood. So the density of blood is officially 1.06 grams per milliliter. So, of these two, who was more accurate, who was more precise, right? Hopefully, you can see that Jacob gets pretty much the same thing every time, but Edward is closer when you take an average, certainly more accurate than Jacob is, but Jacob is more precise. So, we would call Jacob precise, and we would say Edward was more accurate. All right, so that's that. Now, there are errors in measurement. Everything we use that measures things has limitations. And what we have to do is uh, allow the numbers to speak to how well our instrumentation was calibrated for that uh, situation. So, for example, if we're measuring this leaf and the only ruler we have is this ruler, do you understand that we really can't say that this ruler is allowing us to measure this leaf in a very good way? It's not very accurate tool for this. We know that that leaf is somewhere between 3 and 4, but that's all we can say for certain. Okay. So we have to, the way we do it in science, because we have lots and lots of instruments that if we're in lab, you can play around with and see, but we know for certain this leaf is somewhere between 3 and 4. So everything we know, and then we have to estimate one digit past what we can read. So this would be, for example, that's somewhere between 3 and 4. So you could say 3.5. You could not say 3.48 because this is estimating two digits beyond what we know. This is the only one we know, right? And then we're estimating one digit beyond. So here's some more examples. It's a little hard. So for this one, right, we know the 8 and we absolutely know the 0.2. So for sure, we know 8.2. So now we can estimate something beyond that. We can estimate one more place. So it's 8.2. And then maybe we want to say that's pretty far. I don't know. I mean, the point is here, if you put a 5 instead of a 6, if you put a 7 or an 8 instead of a 6, they're all considered correct. You're trying your best. That's why it's an estimate, okay? So the estimated digit is known as a significant figure. All right, so look at this thing. Here's our lousy ruler, and it just has from, this should be 0, actually, not 1. That should be a 0. So between 0 and 10, and here's the halfway mark. So we know this thing is somewhere between 5 and 10. So if we were going to estimate one thing, so we don't know whether it's 6 or 7 or 8. So any whole number we guess is going to be the guess. So we might say that this is, it looks about an 8. Okay, that's the best we can do. That's already a guess, that 8. So that's one significant digit. With this ruler, it's the same thing. Oh, now we know it's between 8 and 9. So we know for certain the 8, and now we can guess one more, and we can say that's maybe 80% of the way over there. So 8.8. So now this is the guess. This is the estimate. This is known. For that one up here, this was already a guess, and that's why we had to stop there. So this had one significant figure, right? Significant figure. And this has two significant figures because there's a better measurement device. Now we get to this one. Look at this. Now we know for certain it's 8.8, I guess. Do we know that for certain? Yeah, I guess so. So now we know that, those two, and the next one we're going to estimate, and we might estimate that as 0. So now this has three significant figures because the instrument we're using has more hash marks. We can read it in a more accurate way, or it's a better tool for this measurement. Okay, so here's some practice. Remember, you got to determine what you know for certain first, and then you're going to estimate one place beyond what you know. So if we had this and that landed there, so we know for certain this is between 50 and it's between, this is 60, so this one must be 55, right? So we know it's between 50 and 55. So we can say for certain the 50. The next thing we're going to do is guess. So I could say 52. You could say 53, 54, whatever you want. But this is going to have two significant figures. You can't go beyond the ones digit because this ruler is already having you guess that 2. Okay? So let's try this one. All right, so in this case, I know this is between 2 and 3 for certain. So I can guess any decimal after 2. I can say 2.1, 2.2, 2.3. Now, obviously, 2.1, all those would be down here. So you want to guess something higher. So you could say 2.9. You could say 2.8. You could say maybe even make an argument for 2.7. But this has two significant figures because of the accuracy of what we can see based on the hash marks on there. And now if we had this ruler and it's there, okay, we know for certain it's between 0.5 and 1. So therefore, we could say 0.6, 0.7, 0.8, 0.9. We couldn't go further than that. So we could say 0. Maybe 7. Okay, we couldn't say 0.75 because we already guessed the 7. This was already estimated. So this has one significant figure because we only know the 0.7. All right, so the point of all this is that numbers communicate the quality of measurement. If you have more digits in your number, then that is more higher quality of a measurement. And you can't just say something that wasn't reflected by the tool you were using. So for example, if I use this flask, and this flask has no hash marks on it, as you can see, it just says it's a 250 milliliter flask. So when full, it's 250 milliliters. No one could say for certain that it's 163.5 mils. It could very well be, but based on this flask as a measuring device, you couldn't say that. That is not true. You can only say it's somewhere between 0 and 250. So you could say it was 100 or 200 milliliters, and that's about it. All right, maybe you could say 50 if it was lower, but you basically can only have one significant digit. Okay, so getting back to this was the problem with this cannon. If you noticed, the cannonball got stuck in the cannon. And the reason was significant figures. Back in the cannon days, the guy who was in charge of cannonballs told his workers, hey, everybody, I need an 8-centimeter diameter cannonball. So they made 8 centimeters, but if they had 8.1 or 8.2 or 8 point, or 7.9, They're still like, well, that's 8 centimeters. That's fine. So they put them all in there. Turns out 8.2, not going to do it. It's going to get stuck and it's going to make the cannon explode. So what the guy should have said is, I need all my cannonballs to be 8.0 centimeters. He should have set it to 2 significant figures, not 1. So by saying 1 significant figure, this thing exploded, went backwards, and it was a Greek tragedy for sure. All right. If he had 8.0, if he said that, then they would have known to throw away the 8.1. They would have known to throw away the 8.2 because it's not accurate to that many places, that they're trying to get it accurate to 8.0, and then the cannonball would go through the cannon. All right. So that is why we do significant figures. There will be times in science, in measurement, whatever, where things need to be a certain accuracy. And if you don't have the number to the number of decimal places, then you're not going to make something as accurate as it needs to be. Okay. So there are rules to significant figures. These are somewhat arduous, and there's an easier way to remember it at the end. Some of you may not like the easier way and prefer this. So I'm going to go through this. If it's not a 0, we consider that number as significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All those digits are not 0, so therefore they're considered significant. A sandwiched 0 will always be significant. So here we have a non-zero number, a non-zero number, and there's a 0 sandwiched in between. So that is still significant, even though it's a 0, because it's between 2 significant numbers. A leading 0 is never significant. So this number here, all these zeros are considered leading. They're not considered significant. They're just getting you to the point where that is. You could have just easily said that's 4 times 10 to the minus 4 and not had any of those zeros, correct? So leading zeros are not considered significant. In fact, there's a saying in Puerto Rico, eros en cero ales. As you can tell, I took French. A l'izquierda. Sounds a lot better when someone says it who can. So anyway, that is an insult to someone. You say you're a 0 to the left, which means you're insignificant. What smart people there are to be making fun of people with significant figures. All right. So rule number 4, trailing zeros. Sometimes they are, sometimes they aren't. If there's a decimal point, they will be. If there's no decimal point, they will not be. So for example, if you only measured this number to 1.45, why would you keep writing zeros unless you actually measured them, right? That is all you would need to write. But if you kept writing a 0, then that means you measured it to this point, but just so happened to be that they were both zeros, and you want to let the world know, hey, I measured it all the way out here. But so those would be considered significant. If there is no decimal, 300, those are not significant. So this 0 and this 0 are not significant. There's only one significant figure on that 300. So the only thing you measured was the 3. You did not measure those zeros. They, again, are just placeholders. You could just as easily write that as 3 times 10 squared, right? So those zeros are just holding places like the leading zeros were holding a place. All right. And then the last rule is conversions are considered infinite in their number of significant figures. So you may want to say, well, this only has one significant figure, but this is a definition. And by definition, these have infinite significant figures. We'll figure out why that's important in a minute here. But even though 1 meter equals 1,000 millimeters, and based on the rules I just told you, this would only have one significant figure because these zeros are after there's no decimal point there, and it's a trailing 0, we would still say this has infinite significant figures because it's a conversion. It's a definition, and definitions have infinite significant figures. All right. So, right. So here's the other way to do this. I left space because everyone loves how I draw the United States. So this is the United States, kids. There it is. Do you recognize that as the United States? I've been told before it looks like a fish, right? So it's like a goldfish. It's the country that smiles back. All right. So let's get to some seriousness here. The United States on this coast has an Atlantic Ocean. right? Hopefully you remember that. And on this coast over here, there's a Pacific Ocean. So if there is a number, let's say 1.0400, okay, if there is a decimal present, then you start at the Pacific side, you start counting at the first non-zero number, and you keep going. So this would have 1, 2, 3, 4, 5 significant figures. Okay, because there is a decimal present and we came from the Pacific side. If, however, I'm going to change my color here a little bit. So let's make the Atlantic Ocean blue instead of red. Okay, so this is the Atlantic. If, however, you're coming from a decimal absent, so a number like 4060, okay, there's no decimal here, so decimal absent, then you start at the Atlantic side and you start counting at the first non-zero number. So you come from this way. In the Pacific situation, when there's a decimal present, you come from this direction. And you always start with the first non-zero number. And then you just keep counting until you get to the end. So this has 1, 2, 3. This has 3 significant figures. All right. So that crazy visual helps with this, and you'll get through this if that makes sense. Or if you like rules, you can just memorize all the rules. But basically, and here it is written here. Okay, when a decimal is present, you start from the Pacific side of things, right? Present, Pacific, 1, 2, 3, 4. This 0 is significant because it comes after a non-zero digit as we're heading in that direction. If there's a decimal absent, you start at the Atlantic, come from this direction, okay? And again, I probably should have changed my pen color, so I'll turn that red. I'll turn this red, right? That's basically what I was saying. All right, so that is where we end here. That's the first of the videos. I hope that's helpful, and thanks for listening.